Hey, so now we're going to see another exercise of related change rates, okay? So here's an exercise that says that a shuttle's coming from here and it's going all the way up vertically. And here's a camera that's always pointing at the shuttle. So first the camera points this way, and then this way, and then this way, okay? Right now the camera is pointing over here to the shuttle. The shuttle's up here. As this camera points to the shuttle, this angle right here increases, okay? This is the angle theta, and it's increasing. This s right here is the function with respect to time that says where the shuttle is going to be according to time t in seconds. So for example, in the first second, the shuttle is going to be at 50, right? Because 1 squared 1 times 50, 50, it'll be at 50 feet. In the second second, it's going to be 2 squared 4 times 50, 200, it'll be at 200 feet. So when as a matter of fact, when t equals 10 seconds, what's going to be the rate of change of the angle of the camera pointing to the shuttle with respect to time? What it's asking for is this, d theta dt. What is this stuff? Okay, when t equals 100. Well, you got to somehow relate this s right here with theta, okay? Now, what can you do? You can see here that this is the right triangle, okay, because this is the 90-degree angles here. So you got to relate this theta right here with this s, okay? Now, one thing that you can do, you could try the sine, but then you have to divide this side by this side. We don't know anything about this side, so no. Okay, it's easier. We could find out, but it's easier. We're just going to find the tangent, because the tangent is going to be this side, the side opposite to the angle, divided by the side adjacent to the angle, which is 2,000 feet. Okay, and this 2,000 feet is always 2,000 feet because the shuttle is going straight up. So we have here the formula that relates these two. It's the tangent of theta equals s divided by 2,000, right? And now all we gotta do is to differentiate both sides with respect to the time, okay? So what we're gonna do, remember, we gotta differentiate this thing here with respect to theta, okay? We gotta differentiate this stuff with respect to theta and d theta dt. Okay, which is what we want. This is just implicit differentiation and the chain rule. So differentiating, I'm just going to do this in here to separate. So differentiating is going to be secant squared of theta, and here you got d theta dt, which is just theta prime. Okay, I'm just going to do theta prime to make it easy. The second thing in here is a function with respect to s, and s is with respect to t. So you could do differentiate this with respect to s times ds dt, okay? So differentiating this s right here with respect is s divided by 2,000. So differentiating this is just going to be 1 divided by 2,000, okay? And then you have s prime, which is ds dt. Now, do we have ds dt already? Yes, we do, because look, this is the formula, okay? So differentiating this stuff with respect to t is going to be 100t. So let's just put 100t in here. Okay, all right. This is going to be a little bit complicated. So when t equals 10, okay, at 10 seconds. So if t is equals 10, I'm just going to replace this t here. 10 times 100 is 1,000. So I'm going to put 1,000 here. Now 1,000 divided by 2,000 is half. So I'm going to erase this stuff and put half. 0.5, yeah. Okay, so now we got to find out the secant, because we don't know what the angle is. The secant. What's the secant? Secant is the reciprocal of the cosine. So let's find the cosine, okay? Okay, so when t equals 10, what is going to be s? The cosine, guys, is going to be 2000, this side, the adjacent side, divided by the hypotenuse. So we got to find out this hypotenuse here. Okay, so here we go. When t equals, now I'm here. When t equals 10, 10 squared, 100, 100 times 50, 5,000. So this thing here is going to be 5,000. Okay. Now, if this is 5,000, this side, I'm just going to put a 5,000 here. When this is 5,000 and this is 2,000, we can find out this. Okay. So I'm just going to call this hypotenuse the h. I'm going to call this h. Usually h in physics is reserved for height, which goes straight up or straight down, but I'm just going to call it h. So h squared equals 5,000 is squared, right? Because you got to square this one plus the square of this one, so it's going to be 25 times 10 to the 6 plus 4 times 10 to the 6. Where's this 4 coming from? Because it's 2,000. You see, it's the square. So it's 5,000 times 5,000. It's 5,000 squared. That'll be 25 times 10 to the 6 plus 2,000 squared. That'll be 4 times 10 to the 6. So h equals the square root of 29 times 10 to the third. Okay? All right. So now you have the hypotenuse. What is going to be the cosine? The cosine of the angle when t equals 10, okay, which is what we want. The cosine of the angle is going to be 2 times 10 to the third divided by the square root of 29 times 10 to the third. So 10 to the third with 10 to the third, you cut it out. But you see, we got the secant squared, so we're actually interested in the cosine squared. So the cosine squared of the angle when t equals 10 is going to be 4 divided by 29, right? But what do we have here? We have here the secant squared, the secant, the reciprocal. So we can say that 29 divided by 4 times the theta prime, which is what we're trying to find out, equals half. Okay? Now what we can do is we're going to pass this thing here dividing, right? Because it's multiplying, so we got to divide. And dividing is just going to be theta prime equals half. I'm going to do this slowly. Times 4 divided by 29. Half times 4 equals 2. So it's going to be equal to 2 divided by 29. What? Radians per second. Second because the time is in seconds, okay? And radians because when you're dealing with cosine and sine and all this stuff, the unit for the angle is radians. It's not degrees. So that's the answer. 2 divided by 29 radians per second. That the rate of change of the angle, it's not the angle, it's the rate of change of the angle when t equals 10. Only when t equals 10, okay? Instinctively, because I already have some experience in this, I know that the change of rate is going to be a maximum at this point right here. At this point, the rate of change of this rate of change of theta with respect to time is going to be a maximum. And as the shuttle goes up and up and up and up and up and just keeps going up, the rate of change is going to approach 0. Okay, let me just do this here so you guys can understand. Let's just say that the thing in here, look, I'm going to put this in here, okay? So here we have the camera and here we have the shuttle, all right? Let's just say now that the shuttle is a little bit upper. Kind of like here. I know what I'm gonna do. I'm gonna get a different color here, and I'm gonna do this. Here, yeah, do this. Okay, good. Just gonna get this little bit over here. There you go. And now I'm gonna do the same thing over here. Okay, I'm gonna put this one on top of the other like that. I'm gonna take it way up there so you guys it can help you visualize this thing. Now you see the distance right here is the same distance right here, okay? But down here, the change in the angle is going to be a lot larger than over here. And I'm going to show this to you guys. So we're going to connect this over here. Okay. And now I'm going to get this, put here. Okay. And now I'm going to get this and go all the way there. There you go. You see, what did I say? I said that over here, down here, which is the same as down here, the rate of change in the angle with respect to time was going to be the greatest. Okay. Now, when it lifts just this much, look at this, the difference in angle here. Okay. The difference in angle was very large. Now, the same red up here is the same red down there. So the linear distance, okay, down here and up there are the same, but up there you can see the difference in angle here is very small. See, look at that. You got a theta here and then you got a theta here. Well, you can see that this theta is a lot larger here than this theta here. This theta here is very small. See, it's like that. Okay. Yeah, see over here, and if you come here, look, it's very small. This distance right here is a lot larger than this distance here. Okay, it's like let me do something here to make it very equal. Let me think here for a second. I'm gonna get a different color like this one, and it's gonna be this distance. Oh man, it'll be this distance. Okay, and now I'm gonna try to imitate this distance here, up here. Let me see. It's gonna be a visual stuff, but kinda, I think they're about the same. Okay, now see, at this distance here, look at this. Look at the change in angle. Now at this distance here, look at that. It's a little tiny thing, you can barely see it. So you see that the rate of change in the angle is gonna be maximum at this point right here, okay? And as the shuttle goes up, the change in theta with respect to time is just gonna get smaller and smaller and smaller. And that's it, guys. So what is the final answer? Hold on. At 10 seconds, okay, after the shuttle went up, when the shuttle is at 5,000 feet from the ground, vertically up in here, the rate of change of theta of the camera looking at the shuttle from the ground all the way up to the shuttle, the rate of change of theta is going to be 2 divided by 29 radians per second.